On the evening of January 26th, 1700, the coast of the Pacific Northwest dropped. Not gradually, not partially. In seconds, hundreds of miles of coastline physically sank several feet. Forests drowned where they stood, coastal villages were erased, and a wall of water launched itself across the entire Pacific Ocean. Western science did not know this happened, not for 296 years. The earthquake had no name in any American or European record, no date, no place in any scientific understanding of this coast. The only written account of what happened that night was recorded 7,500 miles away in Japan, where scribes and samurai noted a mysterious wave arriving at midnight with no earthquake to explain it. They called it an orphan tsunami, a wave with no parent. For nearly 3 centuries, that is all it was, an orphan, unexplained. Then, in the 1990s, scientists working on the Oregon coast found something in the tidal mud that changed everything. The fault that caused this runs 700 miles along the ocean floor, from Vancouver Island in Canada all the way to Northern California, a seam in the earth longer than California is wide, and it is locked right now. Since the night it last broke, the Juan de Fuca Plate has been pressing into North America at 1.6 inches per year. Over 325 years, that movement adds up to approximately 43 feet of pressure stored in the rock with nowhere to go. None of it has been released. When this fault breaks, the shaking will last between 3 and 6 unbroken minutes, longer than most people have ever felt the ground move in their lives. The tsunami that will follow will reach the Oregon and Washington coast in 15 to 30 minutes. Modeled wave heights at the shoreline reach 30 to 100 feet, about 9 to 30 meters. The bridges needed to escape will, in many locations, already be gone before the first wave arrives. FEMA's own working assumption for a full rupture is that everything west of Interstate 5 will be, in their word, toast. The odds of this happening in the next 50 years are, depending on the model, between 1 in 10 and 1 in 3. The odds of Yellowstone producing a super eruption in the same window are near zero. Cascadia is not America's distant geological nightmare. It is its most probable one, and at low tide on the Oregon coast today, if you know where to look, the evidence of the last time it broke is still there, standing in the mud, exactly where it was on the evening of January 25th, 1700. The fault is still there, the pressure is still building, and the story of how a midnight wave in Japan unlocked a mystery that Western science had missed for 3 centuries is one of the most extraordinary detective stories in the history of geology. If you're enjoying these deeper stories about the forces shaping our planet, take a moment to like the video and consider subscribing. Now, let's follow the fault beneath the coast. Far below the Pacific Northwest, two pieces of Earth are meeting in a process that has been shaping continents for millions of years. Subduction occurs when two tectonic plates collide, and the denser plate is forced beneath the lighter one, descending into the mantle and creating the setting for the most powerful earthquakes on Earth. The Cascadia Subduction Zone is the boundary where the Juan de Fuca Plate, a small and dense piece of oceanic crust beneath the northeastern Pacific, is being pushed beneath the much larger North American plate. The contact stretches along the seafloor from Cape Mendocino in Northern California to Vancouver Island in British Columbia, a distance of about 700 miles. Much of the fault lies roughly 50 to 100 miles offshore, far beyond anything visible from the beaches above it. For people standing on the coast, there is no obvious feature marking the boundary. There is no canyon cutting across the ocean surface, no ridge rising into the air, and no visible scar tracing its path. The fault exists as a broad surface deep below the water, where one plate meets another and pressure is transferred through enormous areas of rock. The upper part of this contact is especially important. At depths shallower than roughly 19 miles, friction holds the plates together so firmly that the Juan de Fuca Plate cannot freely slide beneath North America. The oceanic plate continues moving eastward at about 4 centimeters each year, which is about 1.6 inches, according to measurements from satellite geodesy and ground-based positioning systems. The motion continues even while the boundary remains locked. This creates the unusual geometry of a subduction earthquake. The fault is not a narrow crack opening through the ground. It is an inclined surface extending across a tremendous area. When scientists use the word megathrust, they are describing both the mechanism and the scale. Thrust means one plate is being forced upward and over another. Mega refers to the immense size of the fault surface involved. A rupture can therefore release energy across an area comparable to a small country. Earth has produced this kind of earthquake many times. The 1960 Chilean earthquake reached magnitude 9.5. The 2004 Indian Ocean earthquake reached magnitude 9.1. The 2011 Tohoku earthquake reached magnitude 9.0. Each occurred along a subduction zone where one plate was descending beneath another. Cascadia belongs to the same family. Its geology does not require an unusual failure of the Earth to produce an enormous earthquake. The boundary is behaving according to the ordinary rules of subduction. The plates converge, friction holds them together, and strain accumulates across the locked surface. That distinction matters because the danger is contained within a system that appears uneventful at the surface. The ocean remains spread across the fault, currents move above it, and coastal landscapes continue their ordinary rhythms. Far below, however, the Juan de Fuca Plate keeps advancing into the continent, while the locked boundary resists that motion. The machine beneath the coast is already operating. A small motion repeats across the Pacific Northwest year after year. The Juan de Fuca Plate advances eastward beneath North America by about 4 centimeters each year, which is about 1.6 inches. The movement is easy to overlook because any single year's change is smaller than the thickness of many everyday objects. Geological time gives that tiny distance a different meaning. Since January 26, 1700, roughly 325 years of motion have accumulated. Multiplying that interval by the yearly movement gives approximately 43 feet of attempted displacement. That distance does not describe a gap opening beneath the ocean. The plates remain in contact. Instead, the rock around the locked boundary has been gradually deformed as the moving plate continues pressing against resistance. Measurements from positioning stations along Oregon and Washington reveal the same process on the landscape itself. Parts of the coastline are being drawn eastward and downward by several millimeters each year, amounting to only a small fraction of an inch. The change is far too small to notice during a walk along the shore, yet instruments can detect it across repeated measurements. A fixed point on a map is therefore not truly fixed. The crust is shifting as the plate beneath it continues its patient movement. This kind of deformation is described by geologists through elastic rebound theory. Solid rock can bend and store energy when forces act upon it, much like a spring that has been compressed without being released. Strain spreads through the crust, changing its shape while friction keeps the fault from sliding freely. The accumulated deformation also changes the position of the coastline relative to sea level. As the crust is drawn toward the fault, some coastal areas gradually sink. The land can therefore become lower, while the ocean remains at its ordinary elevation, leaving tidal environments increasingly prepared for the effects of a future rupture. The surface records this loading through measurable changes that unfold across decades. When the locked boundary eventually slips, the stored deformation can be released within minutes. The crust near the coast will move in the opposite direction from its long accumulation, springing westward and upward. At the same time, portions of the seafloor above the rupturing fault can rise by an estimated 9 meters, which is about 30 feet. That movement lifts the water above the fault. The first movement of the tsunami begins there, at the boundary between solid earth and the ocean. Water does not need to be pushed by a separate mechanism. The rising seafloor transfers its motion directly into the enormous column above it, creating waves that then spread outward across the Pacific. The 43 feet of accumulated displacement therefore represents something physical and measurable. It is the distance the plate has attempted to move while friction has held the boundary in place. Every passing year adds another small increment to that stored deformation, extending a record that began more than 3 centuries ago. Each measurement adds another mark to that record. Together, they show that the crust is responding to forces far beyond ordinary human perception, preserving a physical history in motion long before any rupture becomes visible. A fault can reveal its character through what it does, and sometimes through what it leaves undone. Along California's San Andreas Fault, thousands of small earthquakes occur each year, allowing pieces of accumulated strain to escape through repeated movements. Cascadia behaves differently. Small earthquakes are scarce along much of its locked interface, leaving the boundary with remarkably little ordinary seismic activity. For generations of scientists, that lack of movement created an awkward puzzle. A major fault was expected to show some regular signs of adjustment. If plates were constantly pressing together, it seemed reasonable that at least some of the strain should be released through minor earthquakes. Cascadia offered very little evidence of that kind. The surface gave the impression of a boundary with almost nothing happening. The explanation reaches into the properties of the Juan de Fuca Plate itself. It is relatively young oceanic crust, and much of the interface where it meets North America has conditions that promote strong friction. Instead of allowing frequent small slips, the contact can hold for long periods. Tiny movements that might occur repeatedly on other faults are suppressed across much of this boundary. That changes the way strain is stored. A fault with frequent small earthquakes can release portions of its accumulated deformation in many separate episodes. Cascadia retains much more of its movement within the crust surrounding the locked zone. The loading therefore continues across decades and centuries, while the landscape above offers little visible indication of how much deformation has accumulated. There is an important refinement to this picture in research published by the University of Washington in 2026. Scientists examined 13 years of ground motion recorded by instruments positioned offshore, allowing them to observe the fault from much closer to the source than land stations permit. The northern portion showed strong evidence of locking, while the central region displayed signs of more complicated behavior, including a period of slow motion and changes associated with fluids moving through the seafloor. These observations do not erase the larger pattern. They add texture to it. Cascadia is not a perfectly uniform surface, with identical behavior from California to Canada. Different portions can respond differently as rock, fluids, temperature, and pressure vary along the boundary. Some areas may release limited strain, while neighboring sections remain tightly coupled. For people living above the fault, that makes the absence of noticeable earthquakes especially difficult to interpret. A decade can pass without any meaningful change being felt at the surface. Another decade can follow it. The same pattern can continue across generations, giving ordinary life plenty of room to establish itself around a geological process that operates on a very different scale. Modern instruments can measure changes that human senses cannot detect beneath the ocean floor, including subtle deformation and movement deep below the sea floor, with increasing precision each year. They can reveal where the boundary appears firmly locked and where portions behave differently. What they cannot provide is a dependable countdown to rupture. Cascadia, therefore, offers an unusual lesson in earthquake science. Activity and danger do not always rise together. Along this fault, the scarcity of small earthquakes is itself part of the geological story, shaped by friction, plate properties, and the long intervals during which strain remains stored in the crust. At midnight on January 27, 1700, the shoreline of Honshu received a wave that had crossed an ocean without bringing an earthquake with it. Japanese records from several coastal communities describe water entering villages, moving boats, and reaching heights of roughly 9 feet. The observations were written down by officials accustomed to documenting unusual waves, tides, and earthquakes, which made the absence of ground shaking especially important. The event acquired a name that captured its strange place in the historical record, Minashigo Tsunami, meaning orphan tsunami. An orphan has a traceable existence, but no known parent, and this wave seemed to fit that description. People had witnessed the water arriving, yet there was no local earthquake to explain where the energy had come from. The records remained on paper, while the source of the wave disappeared into the Pacific. For nearly 3 centuries, the Japanese documents waited without a geological explanation. Then evidence began accumulating on the opposite side of the ocean. Along the Oregon coast, scientists were finding buried marsh soils that had dropped abruptly beneath incoming seawater. The layers contained signs of sudden coastal subsidence, and radiocarbon dating placed several of the deposits around 1700. Some deposits also preserved marine sand above former marsh surfaces, showing that seawater had reached places where it had not belonged before. In 1994, Japanese seismologist Kenji Satake was discussing these findings with United States Geological Survey geologist Alan Nelson during an earthquake conference in California. The possibility that the Oregon deposits and the Japanese wave belonged to the same event provided a way to test the idea with physics. A tsunami generated by a great Cascadia earthquake would have to cross the Pacific at a predictable speed, arrive from a particular direction, and produce wave heights compatible with the historical observations. The ocean itself could therefore serve as a clock, carrying evidence across the Pacific basin from shore to shore. The calculations produced an extraordinary correspondence. A magnitude 9 earthquake along Cascadia on January 26, 1700, could have displaced the seafloor enough to launch a tsunami across the Pacific. The waves would travel at roughly 500 miles per hour in the deep ocean, reaching Honshu about 10 hours after the earthquake. Their predicted arrival and heights matched the Japanese observations closely enough to connect 2 records separated by thousands of miles. The timing provided another piece of the puzzle. Working backward from the documented arrival, around midnight in Japan placed the earthquake on the Pacific coast between roughly 9 and 10 in the evening on January 26th. Historical documents had supplied the arrival. Coastal geology had supplied evidence of sudden subsidence. The physics of tsunami travel connected the two. Then came the indigenous oral traditions of the Pacific Northwest, preserved across generations by several coastal nations. Stories describing violent shaking and a great wave corresponded with the same event recorded in Japanese documents and coastal sediments. Different forms of memory had traveled through different cultures and different centuries, yet they converged on one night in 1700. The orphan tsunami finally had a parent. A wave recorded on the shores of Japan had become the distant signature of an earthquake beneath the Pacific Northwest, allowing scientists to reconstruct an event that had vanished from Western written history while remaining preserved across an ocean. Walk along the Oregon coast at low tide, and pieces of a winter more than 3 centuries ago can still appear between the pools and channels. Dark tree stumps rise from the tidal mud, rooted in positions where living forests once stood. Their presence records a sudden change in the height of the land, preserved in wood and sediment long after the people who witnessed it were gone. When the Cascadia earthquake struck in 1700, sections of the coastline dropped by roughly 3 to 6 feet within moments. Forests growing near tidal wetlands were carried downward into salt water. Trees that had stood above the ordinary reach of the tide were suddenly exposed to conditions their roots could not survive. The trunks eventually decayed, while the submerged bases and root systems remained protected within oxygen-poor sediment. Tree rings provide another layer of precision. The growth patterns preserved inside these stumps show that the trees were alive during the growing season immediately before their deaths. Their final rings place the forest deaths in the winter of 1699 to 1700, matching the season established independently by the Japanese tsunami records. Wood, water, and historical writing had recorded the same disturbance in different forms. The sediments around these forests preserve an even broader history. In coastal marshes, geologists extract narrow cores containing repeated layers called couplets. A dark band of organic marsh soil represents years or centuries of plant growth. Above it, a pale layer of marine sand marks a sudden inundation from the sea. Higher still, another marsh layer records the gradual return of vegetation. One core can contain several of these sequences stacked one above another. Each sand layer represents a separate tsunami deposit, while the abrupt change in elevation recorded by the surrounding marsh shows that the earthquake had lowered the coast. The layers therefore preserve both parts of the event, the movement of the land and the arrival of seawater. Farther offshore, another archive rests on the floor of the Pacific. Earthquakes can disturb unstable sediment along the continental shelf and slope, sending clouds of sand and mud downslope into deeper water. When those deposits settle, they form turbidites. Each layer becomes a timestamp within the ocean floor, preserving evidence of an earthquake that may have occurred hundreds or thousands of years earlier. Radiocarbon dating of coastal deposits and offshore material allows scientists to compare these separate archives. The dates do not form a perfectly regular sequence. Some intervals are short, while others stretch across many centuries. Even so, the repeated pattern is unmistakable. At least 41 major Cascadia earthquakes appear in the geological record of the past 10,000 years, giving an average interval of about 243 years. The southern portion of the margin appears to rupture more frequently than the entire fault in a single event. That detail matters because the layers do more than count earthquakes. They reveal how differently sections of the boundary have behaved through time. Along the shore, a drowned forest may look like a collection of weathered stumps. In the sediment beneath it, there is a much longer record. Soil, sand, roots, and offshore mud preserve separate chapters of the same geological process, allowing the coast to retain memories that human observation alone could never have carried across 10,000 years. There was a strange reversal in the measurements made along the Pacific Northwest coast in 2001. Instruments designed to track ordinary movement showed sections of the land shifting westward for a short time, even though the Juan de Fuca Plate continued pressing eastward. The change was real, yet it arrived without the familiar signature of an earthquake. The movement unfolded over about 15 days. During that period, a deep portion of the Cascadia Fault slipped gradually, releasing energy comparable to a magnitude 6.7 earthquake. Because the motion spread across many days, the ground never produced the abrupt acceleration associated with a felt quake. People above the fault carried on with ordinary life, while instruments recorded the crust adjusting several miles below them. Researchers soon discovered that this was not an isolated event. Looking through earlier measurements revealed a recurring pattern in northern Cascadia. Similar episodes appeared approximately every 14 months, with the land shifting westward as the deeper fault released strain through gradual movement. Each episode lasted days to weeks, giving scientists a new way to observe a part of the subduction system that had previously been difficult to detect. Another signal emerged in 2003. Sensitive seismometers began detecting faint, low-frequency vibrations at roughly the same time as the slow movements. The vibrations were too subtle for people to feel and lacked the sharp character of ordinary earthquakes. Scientists called this signal tremor, and together the tremor and slow movement became known as episodic tremor and slip. The location of this activity makes the phenomenon especially useful for understanding Cascadia. The slow movement occurs deeper than the strongly locked portion of the fault, within a transition zone where increasing temperature and pressure allow the plates to deform in a different way. Rock at these depths can accommodate motion over extended periods, producing a geological rhythm that is measured in days and repeated across years. The deeper movement also interacts with the locked region above it. Scientists continue to study exactly how stress is transferred through this complex boundary, and the relationship is more nuanced than treating every slow event as a direct step toward a great earthquake. The episodes demonstrate that the fault is mechanically connected across different depths, with changes occurring below the locked zone while the shallower portion remains strongly coupled. The pattern has given researchers something unusual for earthquake science, a repeating natural experiment. Every 14 months or so, instruments can observe another episode and compare its location, duration, direction, and strength with earlier events. Instead of relying only on rare great earthquakes preserved in geological layers, scientists can watch the living fault adjust itself through modern measurements. There is a delicate rhythm to these movements. The deep boundary slips, tremor accompanies it, and the upper fault continues carrying the accumulated strain that ordinary surface observations cannot reveal. The cycle has repeated for years, offering a window into the machinery operating inside the subduction zone. Cascadia, therefore, contains two kinds of motion at once. One unfolds gradually in the deep earth, appearing through instruments as a recurring pulse. The other remains stored within the shallower locked boundary, waiting for friction to yield. Together, they show that a fault can move without producing the familiar sensation of an earthquake, while still preserving a continuous connection between the deep and shallow parts of the earth. A rupture along Cascadia would begin at a particular point, then spread across the fault rather than arriving everywhere at once. The first movement could start somewhere in the northern or central portion of the boundary, where the locked surface begins to give way. From there, the rupture would race along the fault at roughly 2 miles per second, allowing a full 700-mile margin to break over approximately 4 to 5 minutes. During that interval, the ground above the fault would continue moving. A large earthquake, lasting 3 to 6 minutes, occupies a different physical timescale from the short jolts people often associate with earthquakes. Buildings experience repeated cycles of motion, and each cycle can add damage to connections, walls, foundations, and structural frames. A structure may withstand an initial period of shaking and become progressively weaker as the movement continues. The character of the motion also changes from one place to another. Near the coast, unconsolidated sediments can amplify ground movement, while areas built on firmer rock may respond differently. In river valleys and filled districts, another process can emerge. Liquefaction occurs when water saturated, loosely packed soil is shaken strongly enough that its grains lose their supporting contact, and the ground temporarily behaves more like a fluid. That transformation can alter the landscape itself. Buildings may settle unevenly or tilt, roads can deform, buried water and sewer pipes can rise toward the surface as the surrounding soil loses strength. Port facilities, foundations, embankments, and buried utilities can all be affected by the same change in the ground beneath them. Seattle, Portland, Tacoma, and many coastal communities contain areas built on river sediments, filled ground, or deposits left by glaciers. These materials vary greatly from place to place, so the shaking would not have a uniform character across each city. A building standing on firm ground could experience a different motion from one located only a short distance away on softer sediment. While structures are responding above, the fault is completing its movement below. The rupture would displace the seafloor across a broad section of the margin, potentially lifting portions of the ocean floor by about 9 meters, which is about 30 feet or more. The exact amount would vary along the rupture, as would the direction and distribution of the movement. That vertical displacement matters because an enormous volume of seawater rests directly above the fault. Even a change measured in feet can disturb water across an immense area when the movement occurs beneath the open Pacific. The seafloor does not need to rise evenly for the disturbance to travel outward. Differences in elevation and rupture direction shape the pattern of the waves as they begin to spread. When the seafloor rises, the water column is lifted with it. Gravity then begins drawing the displaced water outward, creating long waves that spread across the ocean. For people on land, the distinction between these processes unfolds within minutes. The ground movement comes from the fault itself, while the water movement begins as a consequence of the seafloor displacement. The earthquake and the tsunami are therefore parts of one connected physical sequence, separated by only the time required for the ocean to respond. The rupture eventually stops propagating. The shaking fades as the fault finishes slipping, leaving the coastline altered and the ocean already carrying the energy of the seafloor's sudden movement. The last motion of the ground would mark the beginning of a different race, one measured in minutes rather than seconds. Along the Oregon coast, communities such as Seaside, Cannon Beach, Newport, and Lincoln City could have only 15 to 30 minutes before the first tsunami waves arrive. The interval begins while streets are fractured, buildings are damaged, and people are still trying to understand what the earthquake has done around them. A coastal highway follows much of the shoreline, linking communities that depend on bridges and narrow routes through rugged terrain. After several minutes of intense shaking, some bridges could be damaged or unusable, especially where their foundations rest on vulnerable soils. A route that normally carries traffic inland can become a barrier when a crossing has failed. The distance between safety and the ocean may therefore be measured less by miles than by whether a person can move at all. Many coastal bridges in Oregon were constructed before modern seismic design practices became standard. Their vulnerability comes from several sources, including older foundations, ground deformation, and the repeated motion imposed by a long earthquake. Even a structure that remains standing may be unsafe to cross if its approaches have shifted or debris has blocked the roadway. A functioning bridge is a connection between places. A damaged bridge can turn that connection into a dead end. Seaside illustrates the problem with particular clarity. The community has a population of roughly 6,700 people and occupies low ground beside the Pacific. Modeling by the United States Geological Survey shows extensive tsunami flooding across the town, including the central area. Reinforced concrete vertical evacuation structures have been built to provide refuge above the incoming water, but their capacity does not cover everyone who could need them. For some residents, the most reliable route after the shaking may therefore be the oldest one available, their own feet. The Cascadia Region Earthquake Work Group has described circumstances in which coastal residents may have no dependable road evacuation route after a major earthquake. Roads can be blocked, bridges can fail, vehicles can become trapped, and traffic can consume precious minutes. Moving uphill immediately can be the practical path when transportation is no longer dependable. The public guidance for Oregon and Washington places unusual importance on the earthquake itself. Strong shaking lasting more than 20 seconds should be treated as the warning to leave the coast. A phone alert may arrive later. A siren may be damaged, unheard, or unavailable. The ground provides the first signal, and once the shaking ends, the safest response is to move toward higher elevation without waiting for additional confirmation. 15 minutes can sound generous when imagined from a stable room, with roads open and every vehicle ready. On a damaged coast, those same minutes contain obstacles at nearly every stage. Someone may need to leave a building, find family members, cross debris, climb through damaged streets, and reach higher ground on foot. Every delay consumes part of the same shrinking interval. The first wave does not wait for roads to reopen. It approaches while the coastline is still recovering from the earthquake, carrying water displaced by the movement offshore. For those already close to high ground, the available minutes may be enough. For others, the window is measured against every broken bridge, blocked road, and difficult step between them and elevation. Yellowstone occupies a peculiar place in the American imagination. Its caldera, geothermal fields, and record of enormous eruptions have made it a symbol of geological catastrophe, appearing in documentaries, disaster stories, and public discussions of extreme natural hazards. The scale is real, yet the probability of another caldera forming eruption in any given year is estimated at roughly one chance in 730,000. Yellowstone has not produced such an eruption for about 640,000 years, and current observations provide no evidence that another one is building toward the surface. Cascadia presents a very different kind of number. The United States Geological Survey estimates roughly a 10% chance of a full magnitude 9 rupture along the Cascadia Subduction Zone during the next 50 years. Earlier estimates for significant partial ruptures place their likelihood around 37% over the same period, while newer assessments place the chance of a magnitude 8 or greater earthquake in southern Cascadia at roughly 30%. These figures describe probabilities, not predictions of a particular date. They also sit on a human scale. 50 years can fit inside one lifetime, making the statistics much easier to grasp than the immense intervals associated with volcanic supereruptions. A probability near 1 in 3 has an almost ordinary mathematical shape. Imagine a standard die with six sides. Rolling either a 1 or a 2 gives a 1 in 3 chance, close to the estimated likelihood of a significant Cascadia earthquake within 50 years. The comparison does not predict that the event will occur during a particular person's lifetime. It shows why Cascadia belongs in a different category of practical preparation, where an uncommon event can still carry a substantial probability over a span measured in decades. That distinction became part of public conversation in 2015 after journalist Catherine Schultz published The Really Big One in The New Yorker. The article described the consequences of a full Cascadia rupture and quoted Kenneth Murphy, then leading the Federal Emergency Management Agency division serving the Pacific Northwest. His blunt description of the agency's planning assumption became widely repeated, especially the phrase concerning everything west of Interstate 5. The story reached millions of readers and briefly brought the region's geological exposure into everyday conversation. Public attention, however, moves according to a different clock than tectonic strain. A dramatic article can dominate discussion for weeks, while a fault can accumulate deformation for centuries without changing its appearance. The contrast between Yellowstone and Cascadia, therefore, rests on more than eruption versus earthquake. It is a contrast between an extremely rare volcanic possibility and a repeatedly documented earthquake process occurring offshore. The geological record contains evidence for at least 41 major Cascadia earthquakes during the past 10,000 years. Their recurrence is irregular, with intervals that vary considerably, so the average is not a countdown. Still, the record establishes that great ruptures belong to the normal behavior of this plate boundary. Yellowstone's supereruption history belongs to a far longer rhythm. Cascadia's rhythm is measured in centuries, placing its largest earthquakes within the span of recorded human history, where preparation can matter long before the fault moves again. That difference is the number worth remembering, because geological danger is shaped by probability, recurrence, exposure, and the length of an ordinary human life. A distant catastrophe can be enormous and still extraordinarily unlikely. The afternoon of March 11th, 2011, began like many ordinary days along the Pacific coast of Japan. At 2:46 in the afternoon, the seafloor ruptured along the Japan Trench, where one tectonic plate dives beneath another. The earthquake reached magnitude 9.0 and continued for roughly 6 minutes, allowing the rupture to travel across an immense portion of the fault. Its duration offered a tangible example of what sustained shaking can become when a great subduction boundary releases its stored strain. The first tsunami waves reached parts of the Japanese coast in less than 10 minutes. At Miyako, water climbed to about 128 feet, leaving marks far above the ordinary reach of the sea. The wave crossed sea walls, roads, buildings, and harbor structures with a force that transformed familiar coastal spaces within moments. Along the affected shoreline, the earthquake and tsunami became one continuous physical event, first moving the ground and then moving the ocean. The human cost was immense. Japan ultimately confirmed 19,747 people dead or missing, while more than 340,000 buildings were destroyed or damaged. At the Fukushima Daiichi nuclear power station, tsunami water overwhelmed backup power systems, contributing to 3 reactor core meltdowns. The consequences extended far beyond the day of the earthquake, with radioactive contamination requiring prolonged management and cleanup. Japan had spent decades preparing for earthquakes and tsunamis. Coastal communities maintained evacuation routes, warning systems could transmit alerts rapidly, sea walls protected many settlements, and earthquake-resistant construction had become part of modern building practice. Drills taught residents to recognize strong shaking as a reason to move towards safer ground. Maps, signs, shelters, and public education formed layers of preparation around the coastline. Even with those layers, the disaster claimed nearly 20,000 lives. Some people were caught by the speed of the water. Others encountered damaged roads, crowded routes, or waves that exceeded assumptions built into local defenses. Preparation reduced the consequences in many places, yet preparation could not erase the physical scale of the event. The Pacific Northwest begins from a very different position. Much of its coastal infrastructure predates modern understanding of Cascadia. Communities have fewer dedicated tsunami evacuation structures, fewer coastal defenses, and older buildings that were never designed around several minutes of intense magnitude 9 shaking. The region also depends heavily on roads, bridges, and utilities that can be disrupted during the earthquake itself. Federal emergency planning has estimated that recovery from a full Cascadia disaster could require years. For Cascadia researchers, that compressed sequence remains especially valuable because it places abstract models against a documented human event. The lesson is measured in minutes, damaged systems, and the distance between people and safety. Chris Goldfinger, a seismologist at Oregon State University, was in Japan when Tohoku struck. Watching the disaster unfold gave him a direct view of a process familiar from Cascadia research, unfolding on a fault with the same fundamental architecture. The comparison does not mean the two coastlines will experience identical damage. Every community has its own terrain, structures, population, and defenses. Tohoku instead provides something rarer than a prediction. It provides a physical example of what a magnitude 9 subduction, earthquake, and tsunami can accomplish within a single afternoon, offering a scale against which the Pacific Northwest can measure its own readiness. Seattle and Portland occupy safer ground from one part of Cascadia's hazard, yet the earthquake itself does not respect the distance between an inland skyline and the open Pacific. Both cities lie far enough inland to avoid the first ocean surge, while the seismic waves from the rupture would reach them within seconds. Their buildings, roads, bridges, and buried utilities could then endure several minutes of sustained motion. One important effect comes from the ground itself. Seismic amplification occurs when earthquake waves pass through soft sediment and become much stronger than they are on nearby solid bedrock. In some settings, shaking on loose ground can be several times greater than motion recorded on rock only a short distance away. The difference comes from the way sediment responds to incoming energy, allowing certain frequencies of ground motion to become amplified. Seattle contains extensive areas of filled land, river sediment, and deposits left by glaciers. The industrial district, waterfront, and parts of South Seattle include ground that can respond very differently from the bedrock beneath higher neighborhoods. Water trapped within loose sediment adds another concern. During intense shaking, the pressure in that water can rise until the soil loses much of its strength, a process known as liquefaction. Roads can deform, foundations can settle, and buried infrastructure can shift as the ground temporarily behaves more like a fluid than firm earth. Portland faces a related challenge along the Willamette River. Much of the city rests on alluvial sediment, material carried and deposited by rivers over long periods. These deposits can amplify earthquake motion and are particularly vulnerable where groundwater keeps the sediment saturated. Higher terrain around the metropolitan area may respond differently, creating sharp variations in shaking across relatively short distances. The buildings themselves add another layer. Seattle has more than 1,100 unreinforced masonry buildings, many constructed with older brick walls that lack modern seismic reinforcement. Prolonged shaking places repeated stress on masonry, connections, floors, and roofs. A structure that might tolerate a brief earthquake can behave very differently when motion continues for several minutes, especially when the supporting ground is also moving unevenly. Another fault lies directly beneath Seattle. The Seattle Fault is separate from the offshore Cascadia boundary and much shallower. A great Cascadia earthquake could potentially increase stress on nearby faults, raising the possibility of a local earthquake beneath the metropolitan area. Such an event would add concentrated shaking to the regional motion already passing through the city, though scientists cannot determine whether Cascadia would trigger it during a particular rupture. Portland has its own critical weakness in the bridges crossing the Willamette River. These structures connect the eastern and western portions of the city, carrying people, freight, emergency vehicles, utilities, and daily traffic. Many were designed before modern seismic standards. If several crossings became unusable, movement through the city could become severely restricted. At the same moment, hospitals, emergency services, and neighborhoods were trying to coordinate a response. Federal emergency planning has estimated more than 20,000 injuries across the greater Pacific Northwest from earthquake shaking alone in a full Cascadia scenario. That figure excludes tsunami casualties. The most immediate urban challenge would therefore come from the interaction of ground motion, vulnerable sediment, aging structures, damaged bridges, and disrupted systems, all unfolding together across two cities separated from the ocean, yet fully exposed to the earthquake itself. Recovery after a Cascadia rupture would begin with a problem larger than repairing individual buildings. Oregon's Resilience Plan examined the state as a network of systems that depend upon one another, tracing how failures in power, water, transportation, sanitation, and fuel could spread from one damaged component to the next. The difficult arithmetic begins when those connections disappear together, because restoring one service can require another service to function first, creating delays that accumulate across the region for months. Electricity would be among the first losses. Some coastal communities could remain without power for as long as 3 months, particularly where transmission lines cross rivers, steep terrain, bridges, and exposed corridors. Towers may topple, substations may be damaged, and crews could struggle to reach isolated equipment. Restoring one line would therefore depend upon roads, vehicles, fuel, replacement parts, and functioning communications. Drinking water carries a different timetable. Service interruptions could last from 1 month to 3 months because treatment plants are often located near rivers, while distribution pipes pass through ground vulnerable to severe deformation. Liquefaction can shift buried pipes, fracture joints, and disturb reservoirs or pumping equipment. Even where a treatment plant survives, water cannot reliably reach homes if the network surrounding it has been torn apart. Wastewater presents an even longer challenge. Repairing sewage networks could require 1 to 3 years in heavily damaged areas. Pipes buried underground are difficult to inspect, excavate, replace, and reconnect when the surrounding soil has moved in many directions. Sanitation also sets a limit on how densely people can return. A neighborhood may still have standing buildings, yet remain unsuitable for sustained habitation if wastewater cannot be collected and treated safely. Transportation would shape the geography of recovery. The coastal highway depends on dozens of bridges, many constructed before modern seismic standards. If enough crossings fail, the route could become fragmented into isolated sections, Seaside, Lincoln City, and Brookings could find themselves separated from ordinary supply routes, leaving helicopters and boats as vital links for food, medicine, emergency crews, and equipment. Reaching a damaged community would itself become an engineering operation, especially where collapsed structures blocked local streets. Fuel adds another thread to the same web. Storage facilities along the coast are concentrated in low-lying places that can be exposed to tsunami flooding. Facilities damaged by shaking or inundation could lose fuel, contaminate remaining supplies, or become inaccessible. That loss reaches far beyond transportation. Generators need fuel. Excavators need fuel. Ambulances, trucks, boats, and construction machinery all depend upon it. Every repair becomes slower when the machinery required for the repair cannot be supplied. Regional estimates place the human displacement above 1 million people, with economic losses reaching hundreds of billions of dollars. The rebuilding period would therefore extend far beyond the first emergency response, requiring sustained federal assistance and coordination across communities, utilities, transportation agencies, hospitals, and private companies. The arithmetic of recovery has a strange quality. Each damaged system carries its own repair time, yet none exists alone. Electricity depends on access. Water depends on power and intact pipes. Hospitals depend on roads and fuel. Communities depend on wastewater. Supplies depend on bridges. A damaged network can therefore multiply the duration of every other repair, turning recovery into a long sequence of dependencies rather than a single return to normal. The shoreline of Cascadia carries a history measured in layers, each one marking a moment when the land itself changed position. The earthquake of 1700 occupies the uppermost part of that record, close enough to the present for written history to preserve its distant reach. Farther down, older traces form a sequence extending through roughly 10,000 years, allowing geologists to reconstruct a pattern that no single living observer could have witnessed. Offshore sediment provides one of the clearest records. When a major earthquake shakes the continental margin, loose material on the seafloor can slide downslope and settle in deeper water. These deposits, called turbidites, form distinct layers that can be examined and dated. At least 41 major Cascadia earthquakes appear in this archive. Spread across 10,000 years, they produce an average interval of about 243 years, although the spacing between individual events varies greatly. The layers can be arranged into a chronology with names assigned to individual earthquakes. The event designated T, one corresponds to 1700. T2 is placed at approximately 1310, while T3 falls near 1100. Another event, associated with roughly 900, adds another mark to the sequence. These dates gain strength when the offshore layers are compared with evidence along the coast, where sudden land subsidence left recognizable changes in marsh sediments and plant communities. That comparison reveals something important about the nature of the interval between earthquakes. The fault does not release its accumulated strain according to a metronome. Some gaps in the geological record are surprisingly brief, with the shortest known interval near 50 years. Others stretch for approximately 1,300 years. The distribution is therefore broad, and a period of 325 years since 1700 sits comfortably inside the range of intervals preserved by earlier ruptures. Every major event leaves several traces that can be read together. The seafloor records the movement of sediment. Coastal marshes record the sudden lowering of land. Sand carried inland by the resulting tsunami can form another layer above the older marsh surface. Trees rooted along the former shoreline can preserve the timing of the change through their growth rings. Each record speaks in a different geological language, yet their dates can converge on the same earthquake. After an earthquake, the coast begins rebuilding itself. Marsh plants colonize newly lowered ground, sediments accumulate, forests gradually occupy suitable surfaces, and another layer of organic material forms above the disturbance. Far offshore, the sedimentary archive continues to grow as well. The fault, meanwhile, resumes storing strain as the tectonic plates continue their long movement. 41 major earthquakes have been identified in this record. The 1700 rupture, therefore, belongs to a sequence rather than standing apart from it. Counting forward from that event places the present within the 40-second cycle of accumulation, although the geological record offers no calendar date for its completion. That uncertainty is part of what makes the record valuable. It establishes recurrence without supplying a schedule. Past earthquakes show that Cascadia can rupture repeatedly across many thousands of years, while the uneven spacing demonstrates that the intervals cannot be converted into a reliable countdown. The layers preserve what happened, when it happened, and how often the pattern has repeated. They do not reveal the precise position of the present day within the next interval. A map of Cascadia can look deceptively simple. A long boundary offshore stretching from Northern California toward British Columbia. Underneath that line, however, the fault is divided into sections with different structures, histories, and patterns of strain. The distinction matters because an earthquake does not have to involve the entire boundary. Even a rupture that covers only part of the margin can rearrange the distribution of energy across the coast and ocean, producing a pattern very different from a rupture that continues farther along the plate boundary. A rupture may begin within one segment, stop after traveling a limited distance, or continue across the full margin. Far north, offshore Washington and southern British Columbia, the boundary between the Juan de Fuca Plate and the North American Plate is strongly locked across much of the megathrust. The plates continue moving toward one another, while friction prevents them from sliding freely. Strain, therefore, accumulates through long periods. This northern portion is considered a likely place for a rupture to begin if a future earthquake grows into a full margin event. Southward, the structure becomes more complicated around the Gorda subplate, a smaller and more fractured portion of the Juan de Fuca system. Earthquakes occur there more often on smaller scales, revealing a crust divided by additional faults and broken into pieces. Those smaller events can release some accumulated stress locally, while the larger subduction boundary continues storing strain. The southern section, therefore, has its own rhythm, distinct from the more strongly locked territory farther north. The difference becomes especially important when considering the reach of a future rupture. A northern event could concentrate its strongest shaking and tsunami effects toward Washington, southern British Columbia, and nearby coastal communities. A rupture confined farther south could place greater energy toward northern California and southern Oregon. If the rupture crossed the entire margin, the affected coastline would stretch from northern California through Oregon and Washington toward Vancouver Island, linking regions separated by hundreds of miles into one connected earthquake sequence. A useful comparison comes from the Indian Ocean. On the 26th of December, 2004, a magnitude 9.1 earthquake ruptured a subduction boundary beneath the ocean. The rupture extended northward for roughly 900 miles, and the tsunami impacts were strongly shaped by that direction of propagation. Coastal areas facing different portions of the rupture received very different waves, showing how the starting point and travel direction of an earthquake can influence where its energy is concentrated. Cascadia carries the same fundamental physical possibility. The eventual rupture could begin near the northern portion, farther south, or somewhere between them. Its path could remain local or continue across multiple segments. Each additional section that breaks changes the amount of seafloor displaced, the duration of shaking, and the coastline exposed to the resulting tsunami. The geometry of the rupture becomes part of the hazard itself. For this reason, a single earthquake magnitude cannot describe every possible Cascadia future. A partial rupture around magnitude 8 to 8.5 would produce a different pattern from a full margin rupture near magnitude 9 or greater. Scientists can model these possibilities using geological evidence, fault geometry, and physical simulations, yet the precise starting point and final extent remain beyond current prediction. Cascadia is one boundary, but its next earthquake could take several different shapes. Across much of earthquake country, technology can create a small space between detection and impact. California's Shake Alert system, for example, uses sensors along major faults to identify an earthquake after rupture begins and transmit alerts before the strongest waves reach more distant communities. The interval may last only seconds, yet those seconds can allow trains to slow, machinery to stop, and people to move away from immediate hazards. Cascadia presents a different physical problem. The main fault lies roughly 50 to 100 miles offshore, close enough that the first seismic waves can reach the coast almost immediately after rupture begins. For communities less than 30 miles from the fault trace on the seafloor, the distinction between detection and arrival becomes especially small. An electronic warning must be sensed, interpreted, transmitted, received, understood, and acted upon. Each step consumes time, while the earthquake is already moving through the crust. The geology offers little comfort in the form of recognizable advanced signals. Great Cascadia earthquakes do not appear to follow a dependable sequence of foreshocks that would announce the arrival of a larger rupture. The sediment record preserves evidence of many previous events, yet those layers do not reveal a consistent warning pattern immediately before each earthquake. A fault can therefore remain outwardly ordinary until the rupture itself begins. Global positioning system networks provide another kind of knowledge. Their measurements can detect tiny changes in the position of the ground, sometimes only millimeters, revealing that the plates are continuing to converge and that strain is accumulating across the region. Those observations are valuable for understanding how the fault behaves. They have not, however, revealed a specific amount of compression that marks the approach of failure. There is no established threshold at which the measurements turn into a countdown. The same limitation applies to episodic tremor and slow slip, the recurring movements sometimes called slow earthquakes. These episodes unfold over roughly 14 months and occur as part of the normal behavior of the Cascadia subduction system. Their regularity does not provide a dependable measure of how close the locked portion is to rupture. A cycle can pass without a great earthquake, leaving scientists with information about the fault's behavior but no precise appointment on a calendar. That reality shapes the public guidance along the Pacific Northwest coast. Sustained shaking lasting more than 20 seconds is itself the warning. The ground provides the first signal because the coast may be too close for an electronic system to create meaningful lead time. Once the shaking stops, the safest response is immediate movement toward higher ground, without waiting for a siren, a phone message, or an official announcement. For people living near the shore, preparedness therefore begins before the earthquake ever arrives. Knowing which streets lead uphill, identifying sturdy buildings, keeping essential supplies accessible, and rehearsing the first minutes can matter when ordinary communication becomes uncertain. Evacuation routes, elevated ground, household plans, and practice decisions become the few forms of warning that can exist in advance. The limitation is physical, not technological. A fault positioned close to the coastline can rupture faster than a message can travel through a modern network, leaving the first unmistakable signal in the movement of the Earth itself. The mountains of the Pacific Northwest are part of the same geological machinery that strains the seafloor offshore. Far below the coast, the Juan de Fuca Plate bends downward as it enters the mantle beneath North America. Its descent carries oceanic rock and water into increasing pressure and heat, linking two landscapes that can seem unrelated from the surface. Oceanic crust contains minerals that hold water within their structures. As the descending plate is compressed and warmed, those minerals become unstable and release water into the surrounding mantle. The added water changes the conditions of the rock above the slab, lowering its melting point and allowing portions of the mantle to become molten. The resulting magma is lighter than the solid material around it, so it begins a long ascent through the crust. Some of that magma cools underground. Some reaches the surface through fractures and volcanic conduits, building the Cascade Volcanic Arc across Northern California, Oregon, Washington, and British Columbia. Its familiar peaks are therefore expressions of the same subduction process taking place offshore. Mount Shasta, Crater Lake, Mount Hood, Mount St. Helens, Mount Rainier, and Mount Baker belong to this broader volcanic chain. Crater Lake preserves the remains of Mount Mazama, whose great eruption occurred approximately 7,700 years ago. The summit collapsed after an enormous eruption emptied much of the volcano's underground magma system, leaving a deep basin that later filled with water. Its presence adds another layer to the regional story, where the movement of one oceanic plate can shape coastlines, earthquakes, and mountain landscapes across hundreds of miles. Mount Rainier brings the connection closer to Seattle. The volcano stands about 54 miles from the city and rises to 14,411 feet above sea level. Around its summit lies approximately 36 square miles of glacial ice, more than on any other volcano in the contiguous United States. The ice is part of the mountain's beauty, yet it also stores enormous physical potential. If a large section of Rainier's unstable flank collapsed, or if a major eruption rapidly melted and mobilized its ice and snow, the mixture could form a lahar, a dense volcanic mudflow carrying rock, soil, water, and debris downhill. Such flows can travel through established river valleys, including the Puyallup and White River valleys, reaching communities such as Puyallup, Ording, and Tacoma. Their pathways are shaped by gravity and topography, allowing material released high on the mountain to move far beyond the volcano itself. The United States Geological Survey regards Mount Rainier as one of the most dangerous volcanoes in the country because its hazards extend beyond an eruption column. A sudden flank failure could transform ice and rock into a moving current of mud, while a large eruption could add heat and water to the same valleys. The danger is therefore tied closely to the mountain's setting and its stored ice. The geological relationship is therefore unusually intimate. The plate descending beneath the coast helps generate magma far inland, while the same plate remains locked against North America along the offshore fault. One process creates strain along the ocean floor. Another produces the volcanic peaks that mark the continental interior. Earth does not keep these hazards in separate compartments. They are different expressions of a single moving slab, carrying water downward, feeding magma upward, and binding the coast to the mountains through one continuous engine. For the first time, Cascadia is being watched as a living system, rather than reconstructed only from its geological remains. Since the early 2000s, networks of instruments on land and beneath the Pacific have been gathering measurements that reveal how the plates move, strain, and release energy. Together, they form an increasingly detailed portrait of this fault across the margin. Global Positioning System stations provide one of the clearest views. Their measurements can detect changes in ground position on the scale of millimeters, recording the gradual eastward drag associated with plate convergence and the temporary westward movements produced during slow slip. These motions remain imperceptible above ground, while allowing scientists to map where the crust is storing elastic strain. On the seafloor, ocean bottom seismometers add another layer of perception. Land stations sit far from the offshore fault, leaving parts of the earthquake environment beyond their strongest reach. Instruments placed directly on the ocean floor can record seismic vibrations closer to their source, including activity that may be too faint or poorly positioned to appear clearly in the land network. Cabled observatories extend that view through continuous connections to instruments resting over the subduction zone. The Ocean Observatories Initiative, Regional Cabled Array off Oregon, and the Neptune Canada Observatory farther north provide streams of measurements from the seafloor, including pressure observations that can register changes in the overlying ocean. A sudden displacement of the seabed can alter that pressure, giving scientists another way to detect movement at the boundary between ocean and crust. A new University of Washington study, published in 2026, adds an especially useful piece of evidence. Researchers examined 13 years of offshore sensor data, making it the first extended offshore record of this kind for Cascadia. The northern portion showed persistent locking and strain accumulation. Farther south, the central region displayed more complicated behavior, including evidence of slow motion and fluid movement through faults above the plate boundary. The contrast suggests that Cascadia is less uniform than earlier models assumed, with different sections responding to stress in different ways. That complexity changes the meaning of monitoring. The instruments can confirm that portions of the fault remain locked, that the plates continue converging, that slow slip occurs, and that the degree of locking varies along the margin. They can reveal changes in seismic velocity, ground position, pressure, and fluid movement. They can also show where strain is accumulating and where some of the system may be releasing it gradually. What they cannot provide is the one measurement people naturally want most. No instrument can identify the exact moment when the locked zone will fail. The observations cannot yet establish where the next rupture will begin, how far it will travel, whether it will cross neighboring segments, or what magnitude it will reach. Even 13 years of offshore watching leaves that boundary unresolved. The instruments are therefore doing something more modest and more valuable. They are turning an inaccessible fault into a system that can be measured in real time, refining the picture with every passing year. Cascadia can now be observed as strain gathers, fluids move, and different sections respond. The record is becoming richer with every observation, while the timing of the earthquake itself remains beyond the reach of the instruments watching it. At Nescowan, Oregon, the shoreline sometimes reveals a forest that has been waiting in the sand since the winter of 1700. When the tide falls, weathered stumps emerge from the beach, rooted where trees once grew. Their presence records a sudden change in the land itself. During the Cascadia earthquake of January 26th, 1700, parts of the coast subsided, allowing seawater and tides to reach forests that had previously stood above them. Tree ring evidence and radiocarbon dating place the deaths of these coastal trees within the same narrow window as the earthquake. The forest became a geological timestamp preserved where sand and salt water kept its story. Nescowan is especially evocative because the remains are still arranged as a forest rather than scattered as ordinary driftwood. Around 100 Sitka spruce stumps have been documented there, with roots still anchored in the original ground. Their trunks have decayed, while the lower portions endured in waterlogged sediment. A tree that once drew water from coastal soil became evidence of a sudden shift in the shoreline, and the position of its roots preserves the landscape as it existed before the ground dropped. Similar evidence appears across Oregon and Washington. Drowned forests, buried soils, tsunami sand, and layers of marsh sediment occur at numerous coastal sites. The pattern matters because the changes are regional. A single tree can die from disease, storm, or local disturbance. When forests, marshes, and soils across many estuaries record the same abrupt subsidence, the landscape begins to describe an earthquake much larger than any local event. Geological studies show that Great Cascadia earthquakes repeatedly lowered sections of the coast, after which new marshes developed as sediment accumulated again. Willapa Bay became one of the most important places in this investigation. Geologist Brian Atwater examined marsh layers there and recognized repeated couplets of buried soil and younger sediment. Each layer represented a former marsh surface that had been lowered and covered, preserving a sequence of coastal changes. Radiocarbon ages from plant material helped establish when individual layers formed. Tree rings provided another clock, allowing the timing of some forest deaths to be narrowed with greater precision. Atwater's work during the 1980s and 1990s helped transform scattered coastal observations into a coherent earthquake history. By combining stratigraphy, tree rings, radiocarbon dating, and evidence from drowned forests, researchers could identify repeated episodes of sudden land level change. The record at Willapa Bay also helped connect the 1700 earthquake with older events reaching back thousands of years. What had looked like isolated layers became a recurring geological pattern. That pattern eventually reached across the Pacific. The coastal evidence supplied an essential starting point for researchers studying Japanese records of an unusual tsunami in 1700. Kenji Satake and other scientists compared the timing, coastal flooding evidence, and tsunami behavior, helping establish the connection between the Japanese account and an earthquake on the Cascadia margin. The coast therefore carries its history in physical layers that can still be examined. A root system, a buried soil, a tree ring, or a thin band of sand can preserve information for centuries. Together, these fragments form a record written by changing land levels and returning tides, allowing the shoreline to retain the memory of earthquakes long after the forests and marshes have grown back. The map of the Pacific Northwest contains a boundary that seems permanent, yet its existence depends on a plate slowly being consumed. The Juan de Fuca Plate is the surviving fragment of the much larger Farallon Plate, an oceanic plate that once occupied a broad region of the eastern Pacific. Its story reaches back roughly 200 million years when the Farallon Plate began descending beneath North America. Since then, enormous portions of that plate have disappeared into the mantle, leaving only smaller remnants along the western edge of the continent. One of those remnants is the Juan de Fuca Plate. It continues to move beneath North America, carrying oceanic crust toward the mantle and storing strain along the Cascadia Subduction Zone. The same process also supplies material that helps generate magma beneath the Cascade Range. Mountains rise, volcanoes erupt, and earthquakes release accumulated strain within a system whose existence is tied to the slow disappearance of a piece of ocean floor. Offshore, the Juan de Fuca Ridge provides an opposing motion. Along this underwater ridge, molten rock rises and cools, creating new oceanic crust and adding fresh material to the plate. The balance, however, favors consumption. More of the Juan de Fuca Plate is being drawn beneath North America than is being created along the ridge. Its total area therefore decreases across geological time, even while new crust continues to appear at its western edge. The scale of that change is difficult to hold in an ordinary human sense of time. 10 million years ago, the Juan de Fuca Plate was larger than it is today. 10 million years from now, assuming the present tectonic pattern continues, it will be smaller again. The coastline will still exist, forests will still grow, and rivers will still find their way toward the Pacific, yet the machinery underneath them will be changing toward a different arrangement. Eventually, over tens of millions of years, the remaining plate is expected to be consumed. When that happens, the Cascadia Subduction Zone will no longer function as it does today. The great interface, where one plate descends beneath another, will disappear. Earthquakes produced by that particular boundary will cease, and the volcanic system, fed by the descending oceanic crust, will gradually lose its source of magma. The Cascade volcanoes will become geological remnants, their cones and lava fields preserved long after their furnaces have cooled. Such an ending would reshape the meaning of the landscape. The mountains of the Pacific Northwest were not assembled in a single act, and they will not remain unchanged forever. Their elevations, valleys, coastlines, and volcanic centers belong to a moving planetary system whose components are continually created, rearranged, and consumed. Erosion will continue to wear the mountains, rivers will carry sediment toward the sea, and new tectonic relationships may develop where the old boundary once operated. Cascadia, therefore, occupies a particular moment in Earth's history. It has lasted for millions of years, long enough to build mountains, carve valleys, and leave an extensive earthquake record along the coast. Yet, geological permanence is measured differently. A boundary can endure for millions of years and still be temporary. The Juan de Fuca Plate is slowly approaching its disappearance, and with it, one of the engines that has shaped the Pacific Northwest will eventually pass from the landscape into the deeper history of the planet. Across the Pacific Northwest, the scale of Cascadia becomes easier to understand when measured in people rather than fault lines. A full rupture could affect a region containing approximately 10 million residents, stretching from coastal communities in Northern California through the metropolitan centers of Portland and Seattle, and northward into Vancouver, British Columbia. Within that larger population, roughly 140,000 people live in coastal communities located inside the direct tsunami inundation zone modeled for a magnitude 9 event. They occupy places where the interval between the earthquake and arriving water may be measured in minutes. For those farther inland, distance from the ocean changes the immediate danger without removing the earthquake from daily life. Homes, apartments, bridges, hospitals, schools, and businesses remain part of the same regional system. Financial preparation becomes another layer of vulnerability. As of 2026, estimates suggest that only about 15 to 20% of Seattle area homeowners carry earthquake insurance. Most, therefore, remain financially exposed to major structural losses, with recovery depending heavily on savings, assistance, lending, and the broader condition of the regional economy. Public awareness adds another curious dimension. Surveys across the Pacific Northwest have repeatedly found that residents generally know Cascadia exists and understand that a major earthquake is possible. The challenge is therefore less about introducing an unknown hazard and more about how people translate familiar information into personal expectations. A person can understand that a severe earthquake is statistically plausible while still imagining that its consequences belong to some distant future. Risk psychologists describe this tendency as optimism bias, a documented human pattern in which people judge threatening events as less likely to affect themselves than others, even when evidence suggests otherwise. It can operate without denial or ignorance. Someone may follow earthquake news, recognize the geological record, and still postpone securing furniture, storing water, strengthening a home, or reviewing evacuation routes. The mind can hold accurate knowledge and personal distance at the same time. In 2015, the New Yorker article titled "The Really Big One" briefly disturbed that distance. Its vivid account of Cascadia reached a broad audience and won the Pulitzer Prize for feature writing. One phrase from the article became especially memorable, describing the potential destruction west of Interstate 5 in stark terms. For a time, the subject moved from scientific discussion into everyday conversation, giving the region a rare moment of collective attention. Preparedness has improved since 2014. Emergency planning is more visible, public guidance is more familiar, and seismic retrofit programs have expanded in parts of Oregon and Washington. Even so, hundreds of older unreinforced masonry buildings remain occupied, leaving a substantial gap between awareness and physical protection. A building can be familiar for generations, while its structural weaknesses remain unchanged. That gap is where optimism bias becomes most consequential. The geological record does not adjust itself to human schedules, and awareness alone does not strengthen a wall, secure a bridge, or replace an aging structure. 10 million people can know the fault exists while carrying very different levels of readiness into the same future. The difference between knowing and preparing is measured in decisions made long before the ground begins to move. A shoreline can preserve a memory in several forms at once, and along the Pacific Northwest, some of those memories were carried in spoken stories for generations. When geologists began reconstructing the Great Cascadia earthquake of 1700 during the 1980s, they gradually recognized that the landscape was only part of the record. Indigenous nations had retained detailed accounts of the shaking and flooding, offering observations that could be compared with physical evidence rather than treated as folklore detached from science. Among the most striking accounts comes from the Huayat people of Vancouver Island. Their tradition describes a night when the ground moved with such force that people could not remain standing, followed by a great wave that destroyed the winter village at Pachina Bay. The settlement stood low beside the water, and the account preserves a devastating detail. Those present in the village did not survive. Generations later, geological evidence from the same place revealed deposits and changes in the coastal landscape consistent with powerful tsunami flooding. Along the Washington coast, the Quileute people also preserved stories describing violent shaking followed by seawater moving inland. The geographical details mattered. The direction and character of the flooding corresponded with what scientists understood from the physical record, allowing the oral traditions to become another layer in a much larger reconstruction. At least 6 indigenous nations across the Pacific Northwest held traditions connected to the 1700 event. These accounts varied in language and cultural setting, yet several contained specific observations about shaking, waves, damaged settlements, and the behavior of the sea. During the 1990s, researchers began comparing those descriptions with coastal deposits, tree ring evidence, ocean sediment records, and Japanese historical documents. The pieces aligned with unusual precision, down to the timing, the location of affected settlements, and the sequence of shaking, followed by coastal flooding, recorded in the surviving geological layers. The story from Pachena Bay was especially significant because its description of complete destruction could be tested against the coastal geology. Sediments deposited by the tsunami showed that the wave reached far across the low-lying landscape. The physical evidence supported the oral account of a settlement overwhelmed by water, giving scientific weight to observations preserved through memory. There is something distinctive about this kind of record. The knowledge had traveled across nearly 3 centuries without instruments, written measurements, or participation from the scientific institutions that would later investigate the earthquake. People observed what happened around them, remembered the sequence, and passed the account onward. The information survived because it remained meaningful within the communities that carried it. When the evidence is placed together, the 1700 earthquake becomes an unusual meeting point between different ways of knowing. Geological layers preserve the movement of land and water. Ocean sediments record material carried across the seafloor. Tree rings preserve the disturbance written into living forests. Japanese documents preserve the distant arrival of an unexplained wave. Indigenous oral traditions preserve what the event looked and felt like at particular places along the coast. 5 independent lines of evidence converge on the same night. None depends entirely on another to exist, yet their separate records reinforce one another across centuries and across the Pacific. The earthquake left traces in mud, wood, sediment, written history, and human memory, allowing a vanished moment to be reconstructed with extraordinary clarity. Portland and Seattle carry a peculiar inheritance in their streets, foundations, bridges, and buried pipes. Much of what surrounds their residents today was built during the 325 years since the last great Cascadia earthquake. The interval feels long when measured against a human life, yet it is brief beside the geological record. During that span, neighborhoods expanded, roads crossed rivers, reservoirs were constructed, and generations came to regard the arrangement of the ground as a permanent part of ordinary life. Written history in the Pacific Northwest began taking detailed form during the early 1800s, long after the 1700 rupture had faded from living memory within settler society. Portland became incorporated in 1851, while Seattle followed in 1869. The coastal highway network arrived much later, threading through communities that had no scientific record describing how the shoreline had behaved during the previous great earthquake. Engineers and planners worked with the information available to them, building a modern region on foundations whose deeper tectonic history had yet to be reconstructed. That missing history mattered. A city does not need to ignore a hazard deliberately for its buildings to reflect a different understanding of the land. If the record of earlier earthquakes is absent, ordinary assumptions about stability can become embedded in construction practices, transportation networks, water systems, and public institutions. The Pacific Northwest grew during a long interval when the most revealing evidence of Cascadia remained scattered through marsh deposits, coastal forests, ocean sediments, and traditions that scientific institutions had not yet connected. The picture changed during the middle 1990s. The identification of the 1700 tsunami in Japan together with geological evidence from the Pacific Northwest, established that a great earthquake had crossed the region's history. Turbidite studies added another dimension, showing that the event belonged to a much older sequence of repeated ruptures. Suddenly, the long interval of settlement could be placed inside a much larger geological rhythm, and seismic risk began to enter regional planning with a new clarity. Building standards have since become stronger in Oregon and Washington. Modern structures are designed with earthquake forces in mind, using engineering practices that were unavailable to earlier generations. New hospitals, schools, bridges, and other critical facilities can therefore reflect decades of accumulated seismic knowledge. The change is substantial, yet cities are made from layers of construction, and older layers remain in daily use. Across Portland and Seattle, many buildings were completed before modern seismic standards became established. Some vulnerable structures have undergone retrofits, while other improvements remain voluntary or limited to particular categories of buildings. Water lines, transportation corridors, electrical systems, and other networks also contain older components whose replacement requires time, money, and careful coordination. Resilience therefore develops unevenly, one project at a time, across infrastructure built during very different eras. Oregon has set a long-term goal of bringing critical infrastructure towards seismic resilience within 50 years, a timeline that reaches deep into the same statistical interval in which another major Cascadia earthquake remains possible. The region is therefore strengthening itself while living inside the same geological process that shaped its foundations. Every newer structure carries more knowledge than the generation before it, while every older one preserves the physical legacy of a period when the earthquake record had yet to be recovered. A layer of sediment beneath the waters of Puget Sound preserves an unusual possibility from roughly 900 years ago. Around 900 AD, the geological record indicates that Cascadia experienced one of its larger prehistoric earthquakes. In the same broad period, evidence from the Seattle region points toward movement on a separate fault beneath the city. The relationship between those events remains an active area of study, yet the physical traces invite a remarkable reconstruction of how one earthquake might have disturbed another fault system. The Seattle Fault is shallower than the Great Plate boundary offshore. It crosses the region through Puget Sound and passes beneath areas of the modern Seattle metropolitan landscape. Geological studies indicate that it is capable of producing an earthquake of about magnitude 7.3 on its own. Its position gives it a different character from the deeper Cascadia megathrust, because shaking generated directly beneath the urban region can concentrate energy close to the places where people, buildings, roads, and bridges are gathered. Evidence associated with the event around 900 AD includes disturbed sediments near Lake Washington and changes preserved in coastal deposits. These records suggest that substantial deformation occurred across the region during the same general interval as the large Cascadia rupture. Some interpretations propose that the enormous change in stress produced by the megathrust earthquake may have helped trigger movement on the Seattle Fault. The geological evidence supports the possibility of linked activity, although it does not reveal every moment of the sequence with enough precision to establish exactly how the ruptures unfolded. The distinction matters because the two sources would affect the region in different ways. A great Cascadia earthquake could send prolonged seismic waves across the Pacific Northwest, while a Seattle Fault rupture would place a major earthquake source directly within the Puget Sound region. If the two ruptures occurred close together, the shaking experienced around Seattle could be prolonged or complicated by motion arriving from separate faults. Structures already weakened by the first phase could then encounter another pattern of ground movement from a much nearer source. Water adds another layer to the geological record. Around the same prehistoric event, evidence indicates that a submarine landslide occurred within Puget Sound and generated a local tsunami. Such a wave would differ from the tsunami produced by the offshore Cascadia rupture. Its energy would arise inside the enclosed sound, allowing water to move toward nearby shores from a local source. Communities around the basin could therefore encounter coastal flooding generated by processes occurring much closer to home. The 900 AD record leaves an important uncertainty. Scientists cannot yet determine whether this combination of regional megathrust rupture, shallow fault movement, and a submarine landslide was a rare coincidence or part of a recurring relationship. Other Cascadia earthquakes may have produced similar chains of activity, yet the preserved evidence does not provide enough detail to establish a reliable frequency. That uncertainty does not make the scenario imaginary. Its individual elements are grounded in geological observations, and their possible connection comes from studying the timing and distribution of those observations. The landscape around Seattle therefore contains traces of an earthquake sequence that may have involved more than one fault, reminding us that tectonic systems can interact across different depths and distances, leaving several signatures within the same stretch of geological time. After a great Cascadia earthquake, the coastline enters a long interval of repair. The change begins with a sudden lowering of the land, followed by the arrival of tsunami sand across beaches, marshes, forests, and river mouths. Then the living landscape resumes its work. Plants spread through fresh sediment, streams reshape their channels, and new layers gather where older ones were laid down. From the surface, recovery can become so complete that the disturbance seems to fade from the landscape. Coastal marshes are among the first places where this renewal can be followed. Salt-tolerant plants take hold across newly deposited ground, binding loose sediment with their roots. Other marsh plants gradually return, and the community becomes more complex as the surface settles into its new relationship with the tides. A mature marsh can require roughly 50 to 100 years to develop after a major disturbance. During that interval, each season adds another small change to the ground, building an environment that eventually resembles the marsh that existed before the earthquake. Forests follow a different rhythm. When the coast subsides, the forest floor moves closer to ordinary high tides. Some trees can become waterlogged and die, while other areas remain suitable for new growth. Seedlings eventually establish themselves on the lowered surface, creating a younger forest over ground whose position has changed relative to the sea. Centuries later, the living trees may give no obvious clue that another forest occupied the same place before the earthquake. River mouths also respond to the altered coast. A lowered shoreline changes the slope of the final stretch of a river, affecting how water carries sand and mud toward the ocean. Channels can shift, estuaries can widen or contract, and deltas can rebuild in new positions. These adjustments unfold through countless ordinary tides and floods, each one adding a small piece to a landscape that gradually settles into another arrangement. A few human generations can be enough for these changes to become difficult to recognize without geological training. A meadow appears established, a forest seems mature, a river follows a familiar channel. The coast acquires the appearance of permanence through repeated growth and reshaping, even though its position was once altered in a single episode. The older evidence remains underneath. A buried layer of tsunami sand can mark the surface that existed during the earthquake. Drowned tree bases can remain preserved beneath later sediment and younger roots. Farther offshore, a dense layer carried into the deep basin can record the disturbance in seafloor deposits. Each trace occupies its own place in the sequence, separated from younger layers by the gradual accumulation of ordinary sediment. This creates an unusual kind of memory. The surface is always becoming newer, while the ground below retains older versions of the same coast. Rain, roots, tides, and sediment continually revise the uppermost layer, while deeper layers remain protected from that daily rewriting. The forest grows, the marsh matures, and the river finds another course. Yet the sediments preserve the earlier arrangement with a precision that living landscapes cannot maintain for long on their own. The coastline, therefore, carries two histories at once, the one visible in the present and the older one stored in layers beneath it, including the evidence left by the Great Earthquake of 1700. Seattle exists as a concentration of human intention, layered into streets, towers, homes, hospitals, schools, ports, and neighborhoods. The fault below the region has no equivalent for any of these things. It does not distinguish a city from a forest, or a harbor from a stretch of rock. The forces moving through the planet follow relationships established deep inside Earth, while everything built upon the surface occupies only a thin and temporary boundary. Tectonic plates respond to heat rising from Earth's interior, to the circulation of material within the mantle, and to differences in density between slabs of oceanic crust and the surrounding planet. A denser plate can descend beneath another plate, carrying its weight into the mantle. Human presence has no place within that chain of causes. A growing city cannot slow a plate, and a shoreline community cannot negotiate with the movement of rock or alter its direction. The Juan de Fuca Plate has followed this path for millions of years. Its descent beneath North America began before the forests of the modern Pacific Northwest had taken their present form, before salmon occupied these rivers in their familiar abundance, and before mammals resembling those alive today had established themselves across the region. The coast has passed through countless biological eras, while the same broad tectonic relationship continued underneath them. That continuity gives the fault a strange kind of depth. The earthquake that eventually comes will belong to the same geological system that produced earlier ruptures long before people recorded seasons, named rivers, or built settlements. Human history occupies only a small interval within that sequence. Cities can rise, change names, rebuild after fires, and expand toward the water, while the plate beneath them continues along a path measured in geological time. There is no intention in this movement. An earthquake does not select a neighborhood, aim a tsunami toward a village, or arrive as punishment for human choices. The ocean responds to displaced seafloor because water obeys gravity. Buildings shake because the ground accelerates. Slopes fail when their physical stability is exceeded. Each consequence follows a chain of ordinary physical processes connected across distances and depths far beyond the scale of a human life. Seen from that perspective, geological time becomes less like a calendar and more like a different dimension of existence. A human lifetime can contain childhood, work, family, memory, and the transformation of a city. For the planet, those decades pass within processes that began millions of years earlier and will continue long after present coastlines have changed. It places human experience within the larger physical setting that makes the Pacific Northwest possible. Along the coast, this difference can be read directly from the ground. Sediment records former shorelines. Buried forests preserve older ecological worlds. Layers deposited by past earthquakes remain stacked beneath newer soil, each one marking a moment when the crust shifted and the sea responded. The surface changes, generations pass, and communities grow, while the deeper record keeps its sequence. The earth does not know that people are standing there. It does not need to. The same physical laws that shaped this coast before human memory began are still operating beneath it, carrying the Pacific Northwest through a chapter whose duration extends far beyond the lives of those who happen to inhabit it. For generations before instruments arrived on the coast, indigenous communities were already paying attention to the behavior of land and sea. Their knowledge grew from repeated observation, from stories carried between generations, and from careful attention to places where familiar patterns could change. An earthquake was part of that knowledge. So was the sudden arrival of seawater far beyond its ordinary reach. The relationship between the two belonged to lived experience. The Huayot people of Vancouver Island carried memories of the destruction at Pachena Bay through their oral traditions. The Great Earthquake of 1700 remained connected with the loss of a winter village and the arrival of a powerful wave. When the community rebuilt along the coast, the event did not disappear from collective memory. Its details continued through storytelling, preserving information about what the shoreline could do under forces that arrived without regard for human plans. Such traditions served a practical purpose as well as a cultural one. Knowledge passed through spoken accounts can preserve observations about places, seasons, hazards, and unusual events for people who may never have witnessed the original occurrence. A story about land shaking and seawater advancing across a settlement can therefore contain information about the physical behavior of a landscape. Repeated across generations, those observations form a record that remains connected to the people who live within the environment being described. This way of understanding the coast differs from a model that treats stability as the default condition and geological disruption as an occasional exception. The shoreline can provide food, transportation, shelter, and access to familiar waters, while also carrying the possibility of sudden transformation. Those qualities can exist together. Living with the coast means learning its generosity alongside its hazards, rather than separating the two into unrelated parts of experience. When geologists began reconstructing the Great Earthquake of 1700 centuries later, they eventually found that the oral traditions could be compared carefully with physical evidence. Geological layers, drowned forests, coastal changes, and records preserved across the Pacific pointed toward the same event. The stories added another dimension, connecting those physical traces with specific places and remembered consequences. Scientific investigation could measure the ground, date the sediments, and model the earthquake, while the oral record preserved what the event meant at the level of a community. The confirmation that emerged during the 1990s therefore carried an unusual character. Western seismology gained a stronger understanding of Cascadia by recognizing evidence that had already been maintained outside its own institutions. The process translated spoken knowledge into geological terminology, research papers, and hazard assessments. Once expressed through those systems, information that had existed within indigenous communities for generations became legible to agencies, universities, and planners who had previously lacked access to it. There is a long interval between knowing something and having institutions formally recognize that knowledge. Along the Pacific Northwest coast, that interval lasted centuries. The earthquake of 1700 left sediment, damaged forests, altered shorelines, and distant records, but it also left memory among the people who inhabited the coast. That memory survived without seismometers, laboratory dating, or written scientific reports. It endured because people continued to tell one another what the land and sea had already shown them. There is a peculiar kind of clarity in living beside a danger that has already been measured. The Pacific Northwest does not have to imagine that the ground can move beneath its cities. The evidence has accumulated across generations, and the outlines of the hazard have become increasingly precise. People know the name of the fault, the shape of its locked sections, the history of its ruptures, and the physical processes that can send the ocean inland. Modern instruments have added another layer of certainty. Global positioning stations measure tiny changes in the position of the land as the crust bends and releases strain. Seafloor instruments record movements that cannot be captured from shore. Geological layers preserve earlier ruptures, while records from across the Pacific helped establish the timing of the most recent great earthquake. Slow slip events reveal that the fault is active even when no damaging earthquake is occurring. Each method observes a different part of the same system. That kind of knowledge was absent in places struck by famous historical disasters. When Mount Vesuvius erupted in 79, the people of Pompeii had no scientific understanding of the mountain as a dangerous volcano. The Great Lisbon Earthquake of 1755 arrived without a modern seismic network, detailed hazard maps, or a developed theory of plate movement. People lived within landscapes whose deeper behavior remained largely beyond their understanding. Cascadia is different in one important respect. The region has inherited indigenous knowledge describing the behavior of the coast, while modern science has supplied measurements, dates, models, and physical explanations. The two traditions arose through very different paths, yet they meet around the same landscape. The result is an unusually detailed picture of a natural system that still contains one enormous uncertainty. Timing remains outside the reach of present science. Researchers can estimate probabilities across a period of decades, study the intervals between previous ruptures, and identify portions of the fault that are currently locked. None of those measurements can provide a calendar date for the next great earthquake. A society can know that a hazard is real, while lacking the ability to place its arrival on a particular morning, season, or year. That uncertainty changes the nature of preparation. Building stronger schools, reinforcing bridges, protecting water systems, planning evacuation routes, and storing emergency supplies all require decisions in the present for an event that may occur long after the people making those decisions have left their homes or careers. Money spent today produces benefits whose value may remain invisible for generations. The absence of a disaster can therefore make successful preparation look unnecessary, even when the preparation itself is the reason the consequences were reduced. Human institutions are accustomed to responding to visible deadlines. Geological hazards offer something different, a probability spread across time, that makes patience part of resilience. It also makes memory important, because each generation inherits the responsibility of maintaining knowledge that may never be tested during its own lifetime. The fault itself offers no instruction about how to balance those choices. It continues loading through the same physical processes that shaped the coast before modern cities existed. What changes is the human response around it. For perhaps the first time in this region's history, knowledge has reached a point where uncertainty no longer comes from ignorance of the hazard. It comes from the limits of prediction itself. For thousands of years, people have returned to the Cascadia coast after the ground reshaped it. The archaeological record carries traces of that persistence. Layers of discarded shells, fish bones, Tools, hearths, and dwelling materials appear and disappear through time, sometimes interrupted after major earthquakes and coastal flooding. A settlement could lose its familiar shoreline, its freshwater sources, or the ground on which homes had stood. Generations later, another community could establish itself nearby, using the same rivers, beaches, forests, and tidal waters that had drawn people there before. At least 41 great earthquakes are preserved in the geological record across roughly 10,000 years of human occupation. Each event belongs to a world whose people knew the coast through direct experience rather than through modern hazard maps. Their lives followed the rhythms of salmon runs, shellfish beds, forests, tides, and seasonal weather. Those resources made the shoreline worth returning to, even when the landscape had been altered by a sudden descent toward the sea. Archaeologists sometimes find the aftermath in small changes rather than dramatic ruins. A midden may end abruptly. A settlement may shift inland or appear again on higher ground. A familiar path may no longer lead where memory placed it. Such changes can reflect many causes, so researchers read them alongside geological evidence rather than treating every interruption as proof of an earthquake. Where the records align, the human story becomes part of the same layered history preserved in sand, mud, wood, and soil. The pattern reaches into the present. Millions of people now live across the region affected by Cascadia earthquakes and their tsunamis. Cities, ports, farms, roads, schools, hospitals, and neighborhoods have grown around rivers and bays that have supported human life for millennia. Modern communities possess something their predecessors could not have possessed in the same form: a detailed scientific record of earlier ruptures, and a growing understanding of how the coast responds when the fault releases its stored strain. That knowledge does not erase the reasons people remain. Salmon still move through coastal rivers, shellfish still gather in tidal waters, forests still provide timber, shelter, and a landscape shaped by rain and ocean air. The same qualities that have sustained settlement also create strong ties to particular places. Leaving a coastline permanently would mean abandoning more than buildings. It would mean leaving economies, histories, family connections, and cultural relationships that have accumulated across generations. The choice, then, is less about whether human beings will occupy this coast than about how thoughtfully they build within it. A house can be repaired, a bridge can be strengthened, a water system can be redesigned. Emergency plans can be practiced until their instructions become familiar. None of these measures alters the movement of the plates, yet each can change what happens to the people living above them. At Neskowin, old tree stumps remain preserved where a former forest was lowered into the reach of the sea. Their roots belong to a shoreline that existed before the present landscape took its shape. Tides pass around them, season after season, while people continue to live along the coast. The stumps carry the memory of an earlier world, and the communities nearby carry their own memory forward, returning to the same edge with more knowledge than those who came before. 70 miles off the Oregon coast, darkness surrounds a boundary where two enormous pieces of earth meet. More than 1.6 kilometers, which is about 1 mile below the surface, pressure presses into rock. There, the Juan de Fuca Plate continues its long descent beneath North America, carrying with it the accumulated strain of a process that began long before human memory had names for places or years. Since the night of January 26, 1700, the plates have remained locked across much of the Cascadia Subduction Zone. Their motion has never stopped. Heat rising from Earth's interior helps drive circulation within the mantle, while differences in density guide the oceanic plate beneath the continent. The movement is measured in fractions of an inch each year, repeated through every season and every generation. To a person standing on the shore, that motion is too small to notice. Across centuries, its accumulation becomes something much larger. The locked boundary behaves like a surface that can hold strain for a remarkably long time. Rock along the fault can resist movement while the plates continue trying to slide past one another. Stress gathers through that restraint, stored in the deformation of the crust. The process has no visible marker on a beach or in a forest. There is no changing color in the sea, no line appearing across the horizon, no ordinary sign that tells a passerby how much force has accumulated below. Deep within the fault system, episodic tremor and slow slip provide another rhythm. These events can unfold over days or weeks, moving sections of the fault by small amounts without producing the familiar shaking of a great earthquake. They recur on timescales measured in roughly a year or more, and their repeated motion contributes to the continuing complexity of the boundary. Modern instruments can detect these signals. For most of human history, the Earth produced them without an audience capable of recording their passage. Above this machinery, the coastline continues its daily work. River mouths open toward the Pacific. Forests gather rain from the western slopes. Beaches change with storms and tides. Offshore rocks receive the returning water, while old coastal forests remain preserved in places where earlier land was lowered into the reach of the sea. The surface appears to belong to the present moment, even though its position is being shaped by forces operating far below. A span of 325 years is long beside a human life, yet brief within the history of the fault. The same interval can hold several generations, entire cities, changing governments, new roads, and technologies that transform daily life. Underground, the boundary continues its work without recognizing any of these divisions. It stores strain according to physical laws that have no calendar. No clock beneath the Pacific counts toward a particular date. Science can estimate recurrence, measure motion, and identify the conditions that accompany past ruptures, while the exact moment of the next great release remains unknown. The coast, therefore, occupies an unusual place between certainty and uncertainty. The process is real. The accumulated strain is real. The timing remains beyond prediction. For now, the ocean rests above a boundary still holding together. The beaches remain where generations have known them. The rivers continue toward the sea. Far below, rock carries the memory of the last rupture, while new strain gathers around it, one small increment after another.